Welcome to the first class of solid state devices. This class will learn about formation of energy band. So we'll discuss some topics here. Crystal structure of solid. Basically any solid having three types of crystal structure. First one is simple cubic crystal structure, then body centered cubic crystal structure, and face centered cubic crystal structure. Most of the semiconductor in nature are crystalline in form, so we have to understand this crystal structure clearly to understand any type of particular behavior of semiconductor material. Then we'll go for some kind of quantitative calculations for number of electron per cc of any crystal. This will give us a quantitative understanding of density of electrons in a conduction band or valence band. We will discuss that thing later on. Then we will take help from Schrödinger's equation. Any quantum mechanical system can be described by the Schrödinger's equation as the atoms inside any crystal. Quantum mechanical system, some electron means negatively charged particle moving around the nucleus, so can be described by this Schrödinger's equation. Then split of energy bands of any semiconductor material. Basically, we'll focus on semiconductor material here. Okay. So if you consider simple cubic structure, structures look like this. You have 8 number of atoms in 8 corner of this cube. If you have a close look here, then you can find that only on 8th of any atoms is included inside this cube. So atom occupancy of simple cubic system is on 8th times of 8 corner, so it is 1. So one single cube of this simple cubic crystal having one number of atoms. So as many number of cube are there inside some particular volume of crystal, that many numbers of atoms will be there. Fine. So if it is a body centered cubic crystal or BCC crystal structure is like this, just like simple cubic system, except one extra atoms at the center position of this cube. So atom occupancy is again on 8 into 8 plus 1 at the center. So atom occupancy per unit cell is 2. If it is a face centered cubic system of crystal structure, then crystal structure is something different. All the 6 faces of this cube having one hemicircle of atoms, and all the corner having 1 atoms each, and this cube is having 1/8 of the atoms inside this. So total atom occupancy is 1/8 into 8. So it is 1 plus half atoms per each phase. So it is 3. So 1 plus 3 is equal to 4. So number of atoms per unit cell is 4. That is called atom occupancy. We have 3 numbers of 3 types of crystal. On a simple cubic crystal, then BCC and FCC. Now, if we consider on a simple cubic crystal semiconductor, this A is atom to atom distance. That means on atom, center of one atoms to center of the adjacent neighbor atoms, we called A, or interatomic spacing, maybe some value 3 to 7 angstrom. Let's consider some example. A particular semiconductor atoms having interatomic distance 5 angstrom. So its volume is 5 into 5 into 5. So a cube is the volume of this unit cell. If you consider one unit cell, so this is nothing but 125 into 10 to the power minus 29 cc. So number of atoms per 1 cc of crystal is nothing but, if you calculate that on upon this thing, so it is 0.8 into 10 to the power 22 number of atoms per cc. So this much number of atoms per cubic centimeter of crystal. Fine. Now let's consider silicon atoms. Let's consider for silicon atoms having electron configuration like this. Uh, Extremely outermost orbit is third orbit, that is KL and KL M orbit. Okay, so this M orbit is having 2 plus 2 4 number of valence electron. If you consider germanium, it's having atomic number 32. So electron configuration like this, and you know this is again fourth orbit is the last outermost orbit. So having electron, that is valence electron, also 4. So each of the atoms each having 4 number of valence electron. So that many number of atoms per cc having 4 times of 0.8 into 10 to the power 22 atom 22 number of electrons. So never about 3.2 into 10 to the power 22 number of electrons per cc. So can you can have some idea from here how much electron density any semiconductor material may have due to its if it is having simple crystal structure. If it is not simple cubic structure, if it is BCC, then it should be multiplied by 2, and if it is FCC, then multiplied by 4. So you can have huge number of electrons per cc of any semiconductor crystal. Okay. Now, what is Schrödinger's equation? Schrödinger's equation is a linear partial differential equation that describes a quantum mechanical system. If you consider any atom as a quantum mechanical system, because some charged particle is moving here, that is nothing but electron. So that can be described by Schrödinger's equation. Schrödinger's equation is H psi is equal to E psi, whereas H is equal to Hamiltonian. Hamiltonian means this is the total energy operator. Total energy operator means kinetic energy plus potential energy of that system. So if you consider kinetic energy, it is half mv square, means p square upon 2m. P is the momentum. Okay, potential energy is a v. Now p is the momentum is equal to mv. V is the potential energy. So you know if p is the momentum, then p can be expressed by I h cross into del. H cross is h upon 2 pi, normalized Planck's constant, where h is the Planck's constant, psi is eigenvalue. Planck's constant having value, as you know, it is 6.626 into 10 to the power minus 34 joule second, is equal to 4.135 into 10 to the power minus 15 electron volt second. Now if you consider this equation again, h psi is equal to E psi, means what? P square upon 2m plus V is the value of h times of psi is equal to E times of eigenvalue. Fine. So if you rewrite this equation by putting the value of p here, so you will have h cross square del square upon 2m plus V into psi is equal to E psi. So this is equation number 1. Then if you solve this equation number 1, I'm not interested about solving this differential equation here. You can do it by your own. Then value of En is the solution of this equation is nothing but you will have this value m into e to the power 4 divided by 8 epsilon square h square into 1 upon n square, where m is the electron mass having value 9.1 into 10 to the power minus 31 kg for electron. Okay, E is the electron charge 1.602 into 10 to the power minus 19 joule. What about epsilon naught is the permittivity of air. It is 8.85 into 10 to the power minus 12 farad per meter. and on joule is equal to 6.242 into 10 to the power 18 electron volt. Fine. So if you put that value of this m, e, epsilon naught and Planck's constant h here, so you'll have the value of En is equal to 13.4 into 1 upon n square electron volt. So this is basically the orbital energy. En means nth orbital energy En is equal to 13.4 into 1 upon n square electron volt of any atoms. Now if you consider hydrogen atoms, it is having single electron at the first orbit, so value of n is 1, so you will have minus 13.4 electron volt energy for the first orbital electron. Means what? If you want to remove one electron from its first orbit, you have to apply this 13.4 electron volt energy from outside. That's why it is minus. Now if you calculate for different n values, for n is equal to 1, this energy value En is equal to minus 13.4 electron volt. This is the innermost orbit or kth orbit of any atoms. If n is equal to 2, then orbital energy is much more lesser. It is minus 13.4 into 1 upon 2 square, means 1 upon 4. So it is minus 3.35 electron volt for nth orbit. If n is equal to 3, then you will have minus 1.489 electron volt. That means as you move around the outer orbit of any atoms, its orbital energy is getting reduced. That's why it is easier to remove an electron from outer orbit of any atoms, and it is very tough to remove an electron from inner orbit because inner orbit is having higher energy. So so for any atoms, if you have to remove any electron from its orbit, so it must be from outermost orbit. That is extremely outermost orbit called a valence orbit, or this electron is called valence electron. So for if you put n is equal to infinity for here, this equation, solution of this Schrödinger's equation, you will have E infinity is equal to 0. That means somewhere extremely outer position this of any atoms is having 0 energy. But what will be the issue if you consider exactly outside of the atoms? Is it having some energy or is it having some potential? Okay, let's consider the one-dimensional crystal structure here. Exactly any crystal structure is not supposed to be one-dimensional. For convenience, convenience of understanding, we are considering it's a one-dimensional crystal structure. Atoms in the crystal surface look like this, having A as interatomic distance. So as I said, at the far distance places from any atoms having 0 potential, but exactly near position of any atoms is not having 0 potential. It is having some potential. So this is the potential curve, this blue one. So very near position is having atomic potential inside any crystal structure. So maximum potential is around the center of these atoms, and as you move from the atoms to the distant place, this potential is getting reduced here at exactly at the middle position. This is 0 level. Let's consider this is 0 level. Exactly middle position of this A, that means at A by 2 distance you are having minimum potential, and again potential will increase. As you know, potential used to be negative, means it is minus q on q2 upon A. A is the interatomic distance, so potential is basically negative. So we are having some kind of potential wall here. Now what happens? Lesser the value of A, then there will be increased interatomic reactions. Interatomic reactions due to this, the energy, what was the solution of the Schrödinger's equation was explicit energy level. But this explicit energy label became, this idea became obsolete here when you have numbers of interacting atoms. Due to all these interacting atoms, this explicit energy level of any electron orbit gets splitted. This effect is much more fatal for the outermost orbit of the electron, and for the inner orbit of the electrons having some effect as well, but not that much what is observed by the valence electron. So if you consider the issue again here by this graph, this is the interatomic distance and this is number of interacting atoms. So as I said, when number of interacting atoms are more, that means as many number of interacting atoms atoms have, interacting neighbor atoms is having, its energy level of electron is explicit splitted into that many number of parts. So if you have two number of interacting neighbors, if any atoms is having two number of interacting neighbors, its energy layer, that means energy of electron orbit is getting splitted into two number of parts. If interacting neighbor is 3, then it is 3. If it is 4, then 4. Then energy level will get splitted into 4 parts. And as you have lesser value of interatomic distance, the value, the energy split will be that much fatal. That means what? Suppose any electron is moving around the nucleus of any atoms, it is not having some explicit energy level as mentioned by solution of the Schrödinger's equation. Instead of that, it will have a layer of electron energy. So a layer of energy or electron cloud. Within that energy range, electron can have any energy values. So still this this energy value, whatever given by Schrödinger's equation, will be the mean of that energy values. So ultimately the issue is, okay, if you consider other thing here, this is number of interacting atoms and energy level, say particular energy level of E, this is the energy band. So if you have on number of interacting atoms, then it is explicitly on energy level, and if your number of interacting neighboring atoms is getting increased, so your energy level will get splitted, and ultimately you have del E is the energy band. So each and every atoms is having some energy band. Means what? If you have any atoms, say consider silicon atoms, so you will have outermost orbit, and due to other neighboring silicon atoms in that silicon crystal structure, extremely outer orbit of the silicon will get splitted, okay, and it will form a band. Okay, that band is basically for any atoms, regardless to silicon, germanium or anything, extremely outer bond is having some energy band, extremely outer layer is having some energy band. This is really called your conduction band. Now inside this conduction band, the other band is, that means the inner band, exactly the inner band of this valence band is called conduction band, and there is some gap in between this valence band to conduction band, called energy gap. Look here, this eon, this E2 and eon is, E2 is the outermost orbit, orbital energy, and eon is the just inner orbit of orbital energy of E2. So now as this interatomic distance getting reduced, this energy level get splitted. Ultimately, so for some particular energy, per particular interatomic distance, say some particular material is having 2.35 interatomic distance, 2.35 angstrom. So for this material, it is having conduction band energy range like this. You have some valence band here. This is valence band, and in between this conduction band and valence band, you are having some uh, unallowed energy state. This is really called energy gap. If you consider silicon, it is 1.1 electron volt at 200 Kelvin of temperature. So ultimately, uh, what is conduction band? If we summarize this thing, the entire thing here, conduction band is basically the allowed energy state, the allowed energy range for any electron moving to the valence orbit. That means allowed energy range for any electron moving in the outermost orbit. Okay, for the orbit which is just inside the outermost orbit. It is also having some energy range. This is called valence band, and in between this two orbital energy band, we are having some forbidden area where no energy state available for any electron to lie at that energy state. This is called energy gap or forbidden gap. Okay, thank you.